We are Group 1, and our topic is current charge of STT-MTJ fabrications. This is our outline, and first we are going to talk about the size reduction of NTJ, then thermal stability of NTJ, and the manipulation of the structure and the annealing process, and the MTJ in pursuit of high TMR value. And this is my part, size reduction of MTJ. And first I'm going to introduce some characteristics. When we scale down the MTJ, they need to be considered. And first one is critical switching voltage. And RA is the resistance and the area product, and it is exponentially increased with the thickness of the insulating tunnel barrier. Then, second one is the critical switching current and the thermal stability factor. They determine the writing and the retention performance. The critical current is directly linked to the write power consumption, and for high-density memory application capable of 10 years retentions, the thermal stability factor is required to be 80 or higher at room temperature. And this is the equation of the thermal stability factor, and the energy is written like this. From this figure, we know that when the device size reduces, the thermal stability factor will decrease. And so, in order to have a high thermal stability factor, we need to increase the effective anisotropy energy times the thickness value when the size is reduced. Because the energy involved in critical current in imprint is determined by the demagnetization energy, and it is higher than the imprint anisotropy energy, then that determine the thermal stability factor. So imprint has a low switching efficiency. But to overcome this, the perpendicular magnetization was investigated. Both thermal stability factor and the critical current are governed by the same perpendicular anisotropy. The switching efficiency becomes larger. And this is the interfacial perpendicular MTJ with a single interface. When the cobalt boron thickness is very thin, the interfacial perpendicular anisotropy at the interface overcome the imprint shape anisotropy. It is leading to perpendicular z-axis. In other words, if the cobalt boron thickness becomes thicker, and the magnetization will go back to imprint. At this time, the diameter of the MTJ is still about several tens nanometer. And this is the interfacial perpendicular MTJ with double interface. The thermal stability factor realized in this early MTJ was not high enough. So in order to increase the thermal stability factor and continuing the scaling, the effective anisotropy energy times the thickness need to be enhanced. However, the increasing thickness makes the interface anisotropy lower. So to solve this problem, the heavy metal insertion layer is added between the cobalt boron layer to create the interface, and it enhances the interfacial anisotropy. And also, the switching efficiencies is also improved. The double MgO structure allows the scaling down to about 20 nanometer, even 10 to 20 nanometer in diameter, and it is still has a good performance. This is the shape anisotropy perpendicular MTJ, and in this equation, Kb is the bulk anisotropy density, and the Ki is the interfacial anisotropy density, and Ms is the spontaneous magnetization, and the mu0 is the permeability in free space, and the delta n is the difference in dimensionless demagnetization coefficient, and with a disk-shaped free layer favor an in-plane easy axis, but with a bar-shaped free layer enhance the perpendicular anisotropy. So in conclusions, if it is a bar shape, not this disc shape, then the preferred magnetization direction will be perpendicular. And it is the design window for the magnet shape in the free layer. The red part means thermal stability factor is larger than 80, and the blue part means the critical switching voltage is smaller than 0.5, and the overlap region is the region that can achieve highly reliable and low power STT-MTJ. From this figure, we can find that the shape anisotropy and MTJ size can be smaller than the interfacial anisotropy MTJ. All types of MTJ are included in this figure. And for the shape anisotropy MTJ, the magnetic layer can be explored, not limited to cobalt iron boron, because the shape anisotropy determines the perpendicular magnetization, not the interface of cobalt iron boron and MgO. And the shape anisotropy MTJ shows scaling down to the single-digit nanometer, and it still has a high enough thermal stability.
In this part, I'm going to introduce the definition, challenge, and the method to induce higher thermal stability of the MTJ. Here are the four characteristics that MTJs need to satisfy. The first is the high TMR ratio over 100%, and the second is a switching current lower than the corresponding transistor drive current, and the third is the high thermal stability for sufficient retention time. The last one is the annealing treatment stability. Here shows the definition of the thermal stability factor, delta, and it is the energy barrier divided by the Boltzmann constant and the temperature. In different size of the device, the magnetization reversal is mediated by different modes, and in the device smaller than 30 nanometer in diameter, the magnetization reversal is mediated by the rotation mode. This means the energy barrier is the effective anisotropy constant times the surface area of the device and times the thickness. For larger diameters device, the magnetization reversal is mediated by the nucleation mode, and in the nucleation mode, the energy barrier is related to the diameter, thickness, and exchange stiffness constant and effective anisotropy constant. In this page, I'm going to introduce the challenges of thermal stability factor of STT-MTJ. When we scaling down the STT-MTJ, the thermal factor decreases linearly with the area and increase in retention failures. As we know the definition of thermal stability factor, the energy barrier can be related to the anisotropy. And if we want to get the higher value of thermal stability factor, we can increase the energy barrier. But at the same time, we increase the energy barrier, we may increase the ride current together. So we have to choose a proper energy barrier to maintain the thermal stability factor and the ride current. Here shows another challenge of the thermal stability factor is the high temperature performance of STT-MTJ. As we can see in this table, here shows the different applications of the MTJ, and in different applications, the MTJ requires a wide range of operating temperatures. For example, from -40 to 150 degrees Celsius for the automotive application. So in order to compensate for the loss of thermal stability at high temperature, the anisotropy of the device must be increased. And when we increase the anisotropy, it will lead to larger ride currents. And this means that the efficiency of the MTJ will reduce. I'm going to present two papers. They use different methods to solve the challenge of the thermal stability. And the first is the high temperature thermal stability driven by magnetization dilution in CFB free layers for spin transfer torque magnetic random access memory. In this paper, they designed a device which shows in the figure in the right side. As we can see this figure, they put the metallic impurity layer in the middle of the CFB free layer. And from this device, they increase the magnetization dilution and leads to a reduction of the ordering temperature, as we can see in the figure in the left-hand side. In the figure B, we can see that the S1 to S12 are different metallic impurity materials and increasing concentrations from 20 to 40%. So in this figure, we can see that when the concentration increased, the saturation magnetization decreased. Because of the size of the device in this paper is larger, so the magnetization reversal is mediated by the nucleation mode. So the energy barrier is related to the AS, which means the exchange stiffness constant. And the exchange stiffness constant is related to the saturation magnetization. So in this paper, they can varying the impurity material and concentration to modulate the magnetization. And when they modulate the magnetization, they can change the AS, and which can change the energy barrier to achieve higher thermal stability in higher temperature. As we can see in this figure, they can achieve the thermal stability around 40 at temperature around 500 to 550. The second paper is a highly thermally stable sub-20 nanometers emerald based on perpendicular shapes in isotopy. We can see the formula here. The energy barrier is related to the shape and isotropy, and Ks, which means interfacial and isotropy. The last is the KUT, means the magnetocrystalline or magnetoelastic anisotropy, and T means the thickness of the free layer. So in this paper, they want to induce the perpendicular shape anisotropy. So they deposit a thick ferromagnetic layer on the top of the CFB free layer. So they can increase the thickness to achieve the perpendicular shape anisotropy. In the results of this paper, they found that when they increase the thickness of the storage layer here, they found that both perpendicular shift anisotropy and interfacial anisotropy contribute favor out of plane orientation of magnetization. And because of perpendicular shape anisotropy, very high and easily tunable thermal stability factor can be achieved. And you can see the line of 300K here. We can see that we can maintain the thermal stability factor above 16 down to 4 nanometers here. So although we can achieve such high value of the thermal stability factor, there are still many things have to be considered when designing the STT-MTJ. That means when we want to achieve higher thermal stability factor, we must have to consider whether other things like TMR ratio or the right current will be satisfied or not.
And this is my topic, tuning the perpendicular anisotropy by manipulation of structures and annealing process. And let's talk about some strong anisotropy systems. Rare earth transition metals at L sub 10 order alloys and cobalt platinum multilayers. And this system we have talking about this in the class, like a iron platinum systems, and because this crystal structure is strongly deformed along the C-axis, so we can imagine that it has the higher crystal anisotropy along these directions. And for rare earth transition metals and cobalt platinum multilayers, they have the strong interfacial anisotropy. We will talk about it later. So before talking about the PMA, uh, if we want to have a perpendicular magnetization direction at the film, we need to have a perpendicular anisotropy, strong perpendicular anisotropy energies. So PMA value is an energy per area term, which is used to describe the perpendicular anisotropy of the systems. And effective anisotropy constant K effective consists of three terms. First term is the volume anisotropy, consists of crystalline anisotropy and magnetotransition anisotropy and some others. And the second term is the demagnetization factors, is half 4 pi ms squared. And the last term is the interfacial anisotropy terms, is 2ks over t. And the PMA value is the K effective multiplied by thickness, and it's shown like this. And if we plot the PMA value with the film thickness, we'll see that the slope of PMA is negative because the volume anisotropy usually smaller than the demagnetization factors. So at some critical thickness, we will have the negative PMA value, and at this region, we can know the demagnetization dominate this system, so we have the in-plane magnetization. And if the T is smaller than the critical value, then the interfacial anisotropy will dominate, and the magnetization will becomes our plane. And let's talk about the interfacial anisotropy. Let's take cobalt platinum as the example. And the orbit of atoms at the interface will be distorted because the crystal mismatch and some interactions between two different atoms. Just like the picture shown here, this is the interface, and these are distorted atomic orbit, and this will cause effective field HSOI spin orbital interaction field, and this effect can be seen as the crystal anisotropy, but is related to the thickness of the field. If we increase the field thickness, the portion of the distorted atom will decrease, and the demagnetization energy will increase with the volume increase. So this effect will be more significant when the thickness goes down. So this is the density of state of the two magnetization layers. When they are antiparallel, the negative the spin down electrons of the left-hand side is the density is higher, and but the density of state of the right-hand side spin down electron is lower. So the turning current from left-hand side to right-hand side is low, so the resistance is high. But when they are parallel, the spin up electrons is dominant, and there are so many density of state of the spin up electrons, so the turning current will be larger, the resistance will be lower. And there are some electron turning paths, delta 1, delta 5, and delta 2. These three are results from the different band structures, and we can scheme this as three different paths of electrons. And for delta 1, it mostly transports spin up electrons about 100%, and for spin down electron is 0. So the spin up electrons will go through delta 1 to the other side of the magnetization layer. And for delta 2, it mostly transports the spin down electrons about 60%. And if we have the MgO 001 textures and Ferro 001 textures cubic of these structures shown here, we have the density of state of delta 1 and delta 5 and delta 2 like this, and this is the layer number or layer thickness. And as we can see, the density of state of the delta 1 is remain high through the 3 layers, and but for delta 2 is decreased to 0 before touching the outer magnetization site. So when the density when they are parallel, the spin up electron will mostly turn through these 3 layers and causing the high current density and the lower resistance state. And for the spin up antiparallel state, the spin down electrons will decrease to 0 before touching the right-hand side layers. So the turning current will decrease to very low value. So it has the higher resistance state. So the higher resistance state and the lower resistance state of this system causing the higher TMR ratio. So let's talk about some capping layer of tantalum. If we use the capping layer of tantalum below the copper-iron boron, the higher spin orbital interactions of the interface of copper-iron boron and MgO and tantalum, and so increase the PMA value. And the BCC structure of tantalum plays an important role of the seed layer for crystallization of copper-iron boron of 001 textures. And so we need some annealing process to make the amorphous copper-iron boron to be crystallized and to get the BCC001 textures. The picture of the TMR ratio and the annealing temperature is shown like this. We can see that when the annealing temperature goes up, the TMR ratios will goes up to some value about 350 degrees, and this is because the crystallization of the copper iron of BCC001 textures, but over some annealing temperature, this will cause some over annealing effect, and it will deteriorate the structure of the copper-iron boron and MgO and the tantalum copper-iron boron interface. Because the high temperature will cause the boron to diffuse, because boron is the small atom and it has the higher diffusivity, so it can jump into the MgO layer and some other layers like tantalum to destruct the structure of the 001 textures. And tantalum is the same. It will diffuse into the copper-iron boron to deteriorate the structure of it and causing a dead layer.
My name is Zhang Chenrui, and here I'm going to present MTJ in pursuit of high TMR values. So as we know that TMR ratio is the RAP minus RP over RAP. The R is the resistance, and the AP is the anti-parallel state, and P is the parallel state. And with the Julius model, the TMR ratio can be further interpreted as the 2 P1 P2 over 1 minus P1 P2. The P is the number of electrons spin up minus spin up over the sum of the electrons spin up and spin down. So in order to get a higher TMR ratio, we can choose materials with different symmetries of the wave function for spin up and spin down electrons, so that the conductance depending on the overlap of the wave function is very small when the MTJ is in the antiparallel configuration. And secondly, we can adjust the number of bilayer periods and thickness of each layer. And third, we can do so by effective interface modification. So here I'm quickly go through the development of the MTJ and their pursuit of a higher TMR values. Initially, amorphous aluminum oxide was conducted as a tunnel barrier, and the TMR ratio about 70% was achieved. After that, a single crystal MgO was served as the tunnel barrier, and the TMR reaches to 180%. After that, a COFEV MgO COFEV with a pseudo spin valve staking structure was adopted, and the TMR value of 500% was achieved. And after that, with a suppression of TA diffusion through COFEV electrode, a higher TMR up to 600% was achieved. So here, firstly, I'm going to present a paper that uses cobalt, molybdenum disulfide, and graphene, molybdenum disulfide, and cobalt as the MTJ. And here, they use a computational method to simulate this structure, and they reach a TMR up to 1,270%. That is predicted. So actually, numerous experimental and theoretical studies have been conducted considering different materials as the tunnel barriers, but a relatively high TMR was found in Al2O3 and MgO, even though they were able to produce high TMR values, but non-uniform thickness in the device, pinholes, defects, and the trapped charges affect the performance of the devices. So, by using the thin and uniform 2D materials as the tunnel barrier, actually, better control over the morphology of the barrier is possible. So here, firstly, we can see this structure consists of the cobalt MOS2 graphene, MOS2 cobalt, and the MOS2 graphene, MOS2, this multi-layer is served as a tunnel barrier that is sandwiched between two cobalt electrodes. And here, the central scattering region is shown within the two dashed lines, and the remaining parts are the semi-infinite left and right electrodes, so as to reduce the scattering at the lead barrier interface. So here, we can see the spin density plot for the cobalt and MOS2 interface, and the red and the cyan isosurface indicate the positive and the negative magnetization. So here, we can clearly see that the spin densities are induced on MOS2 when it is in proximity to the cobalt electrode. So firstly, we can see the spin-resolved transmission spectrum as a function of energy at the equilibrium condition. And it indicates that the transmission is highly spin-sensitive. We can know that the transmission through the up-spin channel is much higher than that of the downspin channel at the Fermi energy, which confirms that the cobalt electrode is an efficient majority spin injector for the spacer. And here we can see the projected density of states for the cobalt and MOS2 in the cobalt MOS2 interface. We can see that the monolayer MOS2, which is well-known direct bandgap semiconductor material, becomes metallic in the presence of the cobalt. And third, we can see the total current voltage characteristic of the device in the parallel and the anti-parallel configuration. So we can see that the total current flowing through the magnetic junction in a parallel configuration is always greater than that of the anti-parallel configuration, and this difference is significantly increased at higher voltages. And last, we can see this is the SIE, the spin injection efficiency of the device as a function of the applied bias in the parallel and anti-parallel magnetic configuration. And here, the estimated SIE remains very high in the parallel state, and while that SIE is drastically reduced with the increment of the applied bias in the anti-parallel state. So overall, we can see the MR ratio of the device as a function of the applied bias voltage. So here, the MR just shoots as the external bias increases, the MR value also shoots up. And the main reason for such a large MR could be due to the large spin injection efficiency, the SIE here, at the cobalt and MOS2 interface, as it measures the extent of spin polarization in the transport current. And secondly, in this paper, the work reaches 400 TMR at the room temperature in epitaxial FE, MgO, and FE spin wave type magnetic tunnel junctions. Actually, in a widely studied FE, MgO, and FE structure, the first principle calculation has suggested that a TMR ratio of over several thousand %. However, the reported experimental values have barely exceeded 200% at room temperature, and the experimental TMR ratios are extremely sensitive to the state of the FE and MgO interface, since it is difficult to obtain sharp and defect-free interfaces owing to the presence of the lattice mismatch between the iron and the MgO. And such incomplete FE and MgO interface disturb the ideal spin polarized current transport process, leading to the suppression of TMR ratios in experiments. So here in this work, the tuning of the interface states was conducted with magnetron sputtering, electron beam evaporation, and post-annealing and also the natural oxidation. So firstly, we can see is the schematic MTJ stacking structure. Here, we can see the different processing parameters and the layer structure here. And here we can see is the TMR ratio and the I ratio versus the thickness of the MgO layers. And the blue sample indicates the one without chromium annealing. And the black one is with chromium annealing and also a 30 nanometer Fe layer. And the third one is the with chromium annealing and also a 50 nanometer Fe layer. So here, we can see that here has a star, and the star indicates the MTJ with the COFE insertion at the bottom interface with the MgO and the chromium post-annealing conditions. And the COFE inserted MTJ shows a further increased TMR ratio owing to the improved bottom MgO side interface and increased effective tunneling spin polarization by COFE. So here we can see the cross-sectional hard disk stem image of the Fe, MgO, and Fe structure. So we can see a relatively flat Fe and MgO interfaces. And here is the elemental depth profile using the EDS. So we can also see a very desired the result of the elemental mapping. And from this we can see a sharp MgO interfaces and also no significant atomic diffusion from the upper electrode side. So here firstly we can see the normalized conductance spectra for the anti-parallel and the parallel state and room temperature of the MTJs with the 30 nanometer bottom Fe electrode with respect to different bias voltages. They appear almost symmetric, indicating that similar bottom and the top Fe MgO interfaces, nearly independent of the chromium annealing. And it is assumed that such well-tuned bottom and top Fe MgO interfaces were achieved through the fine-tuning of interface conditions, such as the Mg insertion, post-annealing temperature, and also the post-oxidation oxidation. And secondly, we can see the temperature dependence of the TMR, also the R values of the sample. So we can see is the RAP and RP dependence of, and also the structure. And thirdly is the bias voltage dependence of the GAP and the GP at room temperature and also in 3K. The fine structures could be observed only in the GP spectrum, indicated by an arrow and the label A to C. At 3K, two narrow minima and negative and positive bias voltage also appear. So here is the reference of our this presentation. So thank you for your attention.